Okay, now in CCl4, the difference between as I said, the difference between this example and the previous example is that we have here different atoms, carbon and chlorine. So we should carry out a further step to identify the central atom. In the previous examples, all atoms are the same, so there's no difference between them. We can make any one of them as central and outer. But here, which atom is central and which one is outer? I will mention the rule later. So the first step is similar, determining the valence shell electrons. We have one carbon from group 4, and we have 4 chlorine from group 7, so the total is 32 valence shell electrons. Now, which one of is the central atom and which atom is the outer? The rule is that. This is, by the way, the general rule. We have many exceptions, but we will focus on the main rule. Rule of central atom. The central atom is the atom in the molecule that has the least subscript, then the least electronegativity. So the priority for the subscript, if we find that two atoms have the same subscript, then we will check the electronegativity. So in case of CCl4, it's clear that carbon has 1, as the subscript of carbon is 1, the subscript of chlorine is 4, so carbon will be our central atom. Here is carbon, this is carbon, with 4 chlorine around it. The arrangement in Lewis is not important, you can draw them wherever you want. Then draw the sigma bond or the single bond between the central atom and each one of the outer atoms, as you can see here. Out of 32, we distributed 8 bonding electrons, so we still have 24 electrons. As we said, you should go to the outer atoms. Then if you still have remaining valence shell electrons, put them on the central atom. So here 2, 4, 6, and 8. It's octet now. Go to the second chlorine atom, 2 from the bond, 4, 6, and 8, octet. Here is 2, 4, 6, and 8. It's octet, 2, 4, 6, and 8. Our credit contains 32 electrons. Now count how many electrons did we distribute till now? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. So we distributed them all. We don't have any remaining valence shell electrons to be added to to be located on the central atom. Did we satisfy octet for all atoms? Check. Yes, for outer atoms, all atoms are octet. What about the central atom? Count how many electrons we have around carbon. We have 2, 4, 6, and 8. 4 bonds means 8 electrons. So all atoms are octet, so this is the Lewis structure of CCl4. How many sigma bonds we have in this molecule? Yes, we have 4 sigma bonds. 1, 2, 3, 4. We have 4 sigma bonds. How many pi bonds we have? We have 0. We don't have any valence or any pi bonds. How many bonding electrons we have in the entire molecule? Bonding electrons. We have 8 from the bonds. How many non-bonding electrons around the central? Here the question specified the wanted non-bonding electrons. He needs the electrons around the central, not in the entire molecule. Yani around carbon, how many non-bonding we have, how many dots we have around carbon? We have 0. And how many lone pairs we have around central? For sure, it's 0. Another example. Let's draw Lewis structure for water. Same idea, same procedure, same everything. Valence shell electrons. We have two hydrogens from a group 1, and we have one oxygen from a group 6, so the total is 8. Where is the central atom here? The central atom is oxygen because, as we said, the rule states that the central atom, the atom of the lowest subscript, the subscript of oxygen is 1, so it's the central atom. Here is oxygen with two sigma bonds between oxygen and the two hydrogens we have. The credit is 8. We distributed 4, so we still have 4. The rule states that you should go, or you should distribute the outer the remaining valence shell electrons in the outer atom, but the outer atom is here is hydrogen, and hydrogen, as we mentioned, hydrogen contains only S subshell with 2 electrons. So if hydrogen has 2 electrons around it, it will be stable. It cannot accept more electrons. And this is the case here. This hydrogen has already 2 electrons around it from the bond. The same thing for the other hydrogen. So the 4 remaining electrons should be distributed on the central atom. So this hydrogen is stable. This hydrogen is also stable. And oxygen also is stable because oxygen now is octet. How many sigma bonds we have? We have 2 sigma bonds. How many pi bonds? We have 0. How many bonding electrons we have in the molecule? We have 2 bonds, which means 4 bonding electrons. How many non-bonding on the central? Non-bonding on the central atom. How many dots we have on the central atom? We have 4, which means we have 2 lone pairs around the central. This is how to draw Lewis structure of water or for any other molecule. Another example. Draw Lewis structure for carbonate, CO3 minus 2. The valence shell electrons. We have 1 carbon from a group 4. We have 3 oxygens from a group 6. And here, the charge of this anion is minus 2. What does it mean when the charge is minus? What does it mean? Do we have more electrons or less electrons? Yes, minus 2 means we have 2 more electrons. So you should add them to the total valence electrons. So here is 2 from the charge. So the total now is 24. We have 24 valence electrons. Carbon is the central atom. Oxygens are the outer atoms with sigma bonds between them. Distribute the remaining on the outer. So here we have 2, 4, 6, 8. Stop. It's octet. 2, 4, 6, and 8. 2, 4, 6, and 8. We distributed 24 electrons. The credit is 24, so we don't have any more valence shell electrons on the to be distributed on the central atom. And don't forget, here is minus 2, so write it in square brackets. Is it Lewis structure? No, it's not Lewis. Why it's not Lewis? Yes, you are right, because carbon has 6 electrons, while it should be 8. So what shall we do? We have to make one more sharing. One more sharing. From where? From any atom. From this oxygen atom. From which atom? This oxygen in the right, or this oxygen here, or this oxygen there. All are the same. All are the same. So now, so it doesn't matter whether you will make this sharing, this double bond from this oxygen here, from any one of them. Now, if there is no difference in sharing for forming the pi bond, this is called resonance structures. Resonance structures. So resonance structures are Lewis structures that are similar in everything except the arrangement of pi bond. Here, if you make the double bond in the right, then the double bond, the pi bond, you will form it between this carbon here and the oxygen in the right. If you make the double bond with this oxygen here, then this is another structure. If you make the double bond with the oxygen in the left, you will make a third structure. So here we can write three structures that are similar in everything but different in the arrangement of pi bond. This is called resonance structures. Don't forget them. Resonance structure. Don't forget this concept. Now, to save your time in the exam, if the question asked you to write Lewis structure, you can draw one structure, any one of them. But if the question asks you to write resonance structures, then you should draw the three structures or all possible structures. So let's try these three resonance structures for the carbonate anion. When you make the double bond from the right, it will be like this. This is carbon, double bond. Here is oxygen. Here is oxygen 2, 4, 6, and 8. Because we used this lone pair to form the double bond, and we still have these two lone pairs that were not used. This oxygen, we did not use any of its non-bonding electrons, so they will remain the same. This is the first resonance structure. What is the second resonance structure? Yes, you can make the double bond between this carbon here and this oxygen here. 2, 4, 2, 4, 6, 8, 2, 4, 6, 8. Don't forget the charge. This is another, or the second resonance structure. This arrow that has two opposite directions is used to illustrate the resonance idea, to illustrate the resonance concept. So when you draw these arrows with these two opposite directions, it means that you are talking about resonance structures. So this is the third resonance structure here, oxygen and oxygen. And here we have two lone pairs of electrons. So 1, 2, 3. We draw here 3 resonance structure or structures. How many sigma bonds we have? You can take any one of them to make these countings. Any one of them. Here, let's say, let's use structure number 3. Or any one of them will give you the same answers. How many sigma we have in this? We have 3 sigma bonds. How many pi bonds we have? We have 1 pi bond, which is here. 1 pi bond. How many bonding electrons we have? Bonding electrons. Count how many lines we have. We have 1, 2, 3, 4 lines. Each one contains two electrons. So here we have 8 bonding electrons. How many non-bonding electrons around central? Around central. The question specified the non-bonding electrons around central. The central here doesn't have any non-bonding electrons around it, so this is 0, which means we have lone 0 lone pairs of electrons on the central atom. So this is again 0. These are resonance structures and how to draw the resonance structure. As you can observe here, the difference between them is just the arrangement of the pi bonds, where the pi bond is allocated. Again, read the question carefully. If the question just wants the Lewis structure, draw any one of them. But if the question asked you to determine or to write the resonance structure, then you should draw the 3 structures. There is another example on the slide about the resonance structures. It's here, it's nitrate. Try to apply the same idea. For nitrate, for NO3 minus 1. The same idea, same everything. You can draw 3 resonance structures. Now, the next topic in the chapter is something called formal charges. What we mean by formal charges and what's the advantage of formal charges. Formal charges are used if you have two or more possible different Lewis structures. We are not talking about resonance. As we said, resonance structures are equal structures, are equivalent structures. So no difference between them in stability. But all of them have the same stability. But formal charges is applied or are applied. If you draw Lewis structures and you find that you have two totally different Lewis structures. For example, one of them contains two double bonds and one contains one sigma and one triple bond. So in this case, how can we tell which one of these possible structures is more stable, the most stable? The answer is by writing or determining the formal charges. So again, formal charges are applied if you have two or more possible different Lewis structures. So you should determine the formal charges of all atoms to identify the most stable structure. To identify the most stable structure. To illustrate this idea here, I give you example. Let's say you have this model example AB. The total charge of AB is 0 because it doesn't carry any charge here. If nothing is written here, it means that the compound is stable. So this is the compound story is in neutral. So this compound AB is in neutral. The total charge is 0. Now, if you think about it in a logical way, the total charge equal the summation of the subcharges, which means the summation of the charge of A and the charge of B. So 0, it should be the charge of A plus the charge of B. Type. Now, theoretically, what are the possibilities to have 0 net charge? If the charge of A is plus 1, then the charge of B should be minus 1. This is one possible set of formal charges. A second possible set of formal charges is plus 2 and minus 2. So we have many possibilities. If the charge of A is 0, this is another possibility. Then the formal charge of, if the formal charge of A is 0, then the formal charge of B is 0. Which requires less energy? The answer is the zeros. So as you can or as you have 0 formal charges, it means that the stability is maximum and the energy, the required energy is minimum. As the amount of energy decreases, as the stability increases. Plus 1 and minus 1, it means we have one electron to be moved. So it requires a certain amount of energy. Plus 2 and minus 2, it means we require the double amount or twice the amount of the energy. So this is less stable. But 0 and 0, this is the best case because no energy is required at all. So this will give us the best situation. How can we determine these formal charges? To determine the formal charge of any atom, you should apply this rule here. This rule. Look, the formal charge of atom A equals the valence shell electrons around atom A. You can determine it from the number of the group, minus, in square brackets, number of non-bonding electrons around atom A, yani the number of dots, plus half the number of bonding electrons around atom A. Non-bonding electrons around A, it means you should count how many bonds you have and divide them or multiply them by half. Let us illustrate this principle on a real example. Draw all possible Lewis structures, then determine the most stable one. The question asks you to determine the most stable structure, then directly you should think about the formal charges. We may need formal charges here. Carbon dioxide. This is our first example. In carbon dioxide, we have one carbon from group 4, and we have two oxygens from group 6. So the total is 16. We have 16 valence shell electrons. Draw the carbon in the center because it's the central atom with two oxygens around it. Start with sigma bonds. Then check whether you will need more bonds or not. So here we have 2, 4, 6, and 8. 2, 4, 6, and 8. The credit is 16. We already distributed 16, so we don't have any remaining valence shell electrons around carbon. Is it possible Lewis structure? Is it correct possible Lewis structure? No. This is incorrect Lewis structure because as you can see, carbon has 4 electrons around it while they should be octet, they should be 8. So how many more bonds we need around carbon? Yes, you are right. We need 2 more bonds. Now the question is, give me the possibilities. How can we draw these 2 bonds, the two bonds that we need? Yes, the first possibility, we can make a double bond from the right and another double bond from the left. Here we have 2, 4, 6, and 8. 2, 4, 6, and 8. So this is the first possible Lewis structure. Do we have another possibility? Yes, we have another possibility. We can draw the triple bond or the 2 more bonds that we need from one side, either from the right side or from the left side. They are the same. If we draw them from the left side, from the right side, it will be like this. So here we have 1 lone pair, and here we have 3 lone pairs of electrons. Or we can make them from the left side, the triple bond from the left side. No difference, by the way, in stability between these. These are resonance structures. And as we said, resonance structures in this chapter, we mean by resonance structure the equal structure, the equivalent structure. So in terms of stability, no difference between them at all. Here, just the arrangement is different. And here is 2. So which one of these structures is the most stable? How can we tell which structure is the most stable? Yes, you are right. The formal charges. If you have 2 different or more Lewis structures, then to identify the stability, I should determine the formal charges. To determine the formal charges, you need to determine the formal charge of each atom to form a set of formal charges. Then compare the sets you have. The set that includes more zeros or that are closer to 0, it's the most stable case. Now determine how many valence shell what's the formal charge? Let's give it this abbreviation, formal charge. What is the formal charge of this oxygen? Here is the law. Formal charge in the previous slide, it is the number of valence shell electrons around the atom. We are dealing with this oxygen. The number of valence shell electrons is 6. It's from group 6 minus. Open square bracket. The number of non-bonding electrons around this oxygen, how many non-bonding, how many dots we have around it? We have 2. So this is 2 plus half. How many bonding electrons around this oxygen we have? The bonding electrons, we can take them from the bonds. How many bonds we have around this oxygen? We have 1, 2, 3 bonds, which means we have 6 bonding electrons because each bond contains 2 bonding electrons. Each bond contains 2 bonding electrons. So here 3 bonds, which is 6. Half 6 is a 3. 3 plus 2, 5. 6 minus 5 is a plus 1. So the charge of this, the formal charge of this oxygen is a plus 1. Apply the same rule to determine the formal charge of this carbon. Carbon from a group 4, so we have 4 valence electrons minus square brackets. How many non-bonding electrons we have around this carbon? How many dots we have around it? We have 0 plus half. How many bonding electrons around this carbon? We have 1 bond from the right and 3 bonds from the left. So we have 4 bonds, which means 8 bonding electrons. Half times 8 is 4. 4 plus 0 is 4. 4 minus 4 is 0. So the charge of this is 0. No need to apply the rule for the third oxygen here. No need to apply it. You can directly get it. How? Do you know how? We explained that the summation of formal charges must equal the total charge of the molecule. CO2 is a neutral. It has a zero net charge. So the summation of these three formal charges should be zero. It must be zero. Plus 1 plus 0 is a plus 1. So what is the charge of the third oxygen that makes the net charges 0? It's minus 1. It should be minus 1. Minus 1 plus 0 minus 1 plus 1 is 0. Okay? Or you can apply the rule, it's up to you. But for simplicity, I think this method is better. Now, for this structure, they are the same. What's the difference? The difference is the arrangement. The minus 1 here in the left, plus 1 in the right, and 0 in the middle. No difference between them. Now, check this structure. What's the formal charge of this oxygen? It's in group 6, minus. How many non-bonding electrons we have? How many dots we have? We have 4, plus half. How many bonding electrons we have? We have 2 bonds, which means 4 bonding electrons. Half times 4 is 2. 2 plus 4 is 6. 6 minus 6 is 0. So the formal charge of this is 0. What about this carbon? This carbon in group 4 minus, it has 0 non-bonding electrons around it, plus half. We have 1, 2, 3, 4. 4 bonds, which means 8 bonding electrons. Half times 8 is 4. 4 minus 4 is 0. So this is also 0. So definitely this third oxygen is 0. Which is the best structure? 0, 0, 0, or plus 1, 0, minus 1? Yes, you are right. As we have zeros in our structures, not more zeros, as we are closer to zeros, then the structure will be most stable. This is why this is the most stable Lewis structure of carbon dioxide. I hope it's clear. Let's take another example. CnO minus 1. Here the question asks you to make, as a hint, make nitrogen the central atom. It's an exception to the rule because the rule of the central atom is the lowest subscript. Here, each one of them has the least has the same subscript 1 1 1. The rule said if the subscripts are the same, then you should check the electronegativity. The least electronegative atom is the central atom. If we apply the rule, then carbon should be the central atom because carbon has the least electronegativity. But as exception, the question asked you to determine or to make nitrogen in the central. Now, in the exam or the question, if we don't mention any exception or any hint, then apply the rule, make carbon central. But if the question provides any detail about the central atom, then you should apply the hint or you should apply the requirement of the question. Valence electrons, we have one carbon from group 4, and we have one nitrogen from group 5. Sorry, we have also one oxygen from group 6, plus 1 from the charge. Don't forget, minus 1 means we have one more electron, so the total 6 plus 5 is 11. 11 and 4 is 15, and 1 is 16. Nitrogen is the central atom, according to the question. Here is oxygen, and here is carbon. Start with the outer atom, 2, 4, 6, and 8. 2, 4, 6, and 8. Don't forget the charge, it's minus 1. It's incorrect Lewis structure because nitrogen has 4 while they should be 8, then what are the possibilities? Give me the possible Lewis structures of this. The first possibility, we can make double from left and double from right. Yes, so here is carbon, double, nitrogen, double, oxygen, 2, 4, 2, 4. The second possibility, we can make a triple from the oxygen side. Here is, sorry. We can make a triple from the oxygen side. Okay. Here is not, sorry. Here is nitrogen, triple oxygen, and single bond from the carbon side. Single bond from the carbon side. The third possibility, we can make the triple from where? From the carbon side. So it will be carbon, triple bond, nitrogen, single bond, oxygen, -1. Which one of them is most stable? What should we do? Yes, you have to determine the formal charges. Um, Now, for simplicity, I'll give you I'll give you the values of the formal charges. I'll give you these values, but check them, apply the previous rule for the formal charges, and find them by yourself. For this oxygen, it's 0. For this nitrogen, 1, 2, 3, 4, 5 minus 4 is +1. Then this should be what? Yes, it should be -2. -2 plus 1 is -1. -1 plus 0 is -1, which is the total charge of our molecule. So this is 0 plus 1 and -1. Now let's do this. For this oxygen, don't forget here the 2 lone pairs of electrons. Here we have 2 missing lone pairs of electrons, while here we have 2, 4, and 6. Here we have 2, 4, and 6, and here we have 2. So for this oxygen, it's a +1. For this nitrogen, it is also +1. 1, 2, 3, 4, 5 minus 4 is a +1. This is 1, 2, 3, 4, 5, 6, 7. 4 minus 7 is -3. -3 plus 1, -2. -2 plus 1 is -1. So again, here we got the net charge. For this structure, this is -1. 1, 2, 3, 4. This is +1. So this should be what? It should be -1. 1, 2, 3, 4, 5. 4 minus 5 is -1. Which set of these formal charges, +1, sorry, 0 plus 1 minus 2, or +1 plus 1 minus 3, or -1 plus 1 minus 2 is closest to 0? Yes, you are right. This is the closest to 0. Add the integers here because +1 -1, we are in the range between +1 and -1, while here we have -3, directly excluded. Here we have -2, directly you can exclude -2 and -3. So this structure is the most stable Lewis structure for this molecule, for this example, the most stable. This is how to use formal charges to identify the most stable Lewis structures. The next topic in the chapter is exceptions to the octet rule. Exceptions to the octet rule. From the title, we can conclude that some atoms do not obey the octet rule, which means they may have more than 8 electrons around them, or they may be stable with less electrons around it, less than 8 electrons around them. So when we say exceptions, actually we are talking about the central atom. Please don't forget it. Here we are talking about the central atoms. Central atoms. Exceptions to the octet rule for the central atom, not the outer atoms. The outer atoms are always octet. But the central atom, sometimes they can make or they can take more than 8 or less than 8. This is what we are talking about. If the central atom is stable with less than 8, then we call it incomplete octet rule. Incomplete octet. While if the central atom is stable with more than 8, it's called expanded octet. What are the atoms, the central atoms that are stable with less than 8 electrons? We have two atoms, beryllium and boron. If beryllium has 4 electrons, it will be stable. If boron has 6 electrons, it will be stable. For example, BeH2. When you draw Lewis structure of BeH2 applying the previous methodology, it will be like this. Can you see it here? Now count how many electrons we have around beryllium. We have 4 electrons because we have 2 bonds. So this is 4. It's stable. Another example, BCl3. When you draw Lewis structure for BCl3, it will be like this. How many electrons we have around boron? We have 6 electrons. So again, this is stable according to these exceptions. The second type of exceptions is the expanded octet. Expanded octet. What are the central atoms that can take more than 8 electrons around them? Look, let me redraw the periodic table again here. Here is the periodic table. And okay, this is N1. Here is N1. N1 means we have only S subshell, so they can take 2 electrons around them. If you go to the second row or the second period, here is N equals 2. So here we have S and P. S takes 2, P takes 6, so the total is 8. So any central atom from the second row or the second period in periodic table, these atoms here, they must obey the octet rule with no exception because they have only S and P subshells. So these atoms obey octet rule. طيب, what if we have a central atom from the third period, from here, for example, here, N is 3 or N is 4 or here. When N is 3, we have S subshell, P subshell, and D subshell. S takes 2, P takes 6, and D takes 10. So theoretically, these atoms from third period, they can take up to 18 electrons. It doesn't mean they will take 18, but I am talking theoretically. They can take up to 18 electrons due to the presence of the D subshell. So expanded octet rule are the central atom with more than 8 electrons. What are these atoms? Any atom from period 3, or below, from period 3 or period 4 or below. Example. These are the incomplete octet. We already did these two examples, but look at this. Sulfur tetrafluoride. In sulfur tetrafluoride, when you draw Lewis structure, you will find or you will get this structure. Count how many electrons you have around sulfur. You have 2, 4, 6, 8, and these two lone pairs of these two non-bonding electrons, so the total is 10. Is it stable? Yes, it's stable because sulfur is here. Can you see where is sulfur? This is sulfur. This is N1. Here N is 1. Here N is 2. And here N is 3. So sulfur from period number 3, which means it has S and P and D. So if it takes, we don't have problem at all if the number of electrons on sulfur is more than 8 because it can take more than it. SBR5, this is the structure of SBR5. Count how many electrons you have around AS. You have 2, 4, 6, 8, and 10. 10 electrons. 10 electrons around it. So again, it's stable. It is stable because it's from period number 3. Here are another examples. Draw Lewis structure for each of the following. For BF3, this is Lewis structure for BF3. How many electrons you have around boron? Yes, 6 electrons. Stable or unstable? Yes, it's stable because boron, it's related to the exceptions, to the incomplete octet. So 6 electrons around boron makes it stable. BCl5, this is Lewis structure of BCl5. How many electrons you have around it? You have 2, 4, 6, 8, and 10. Stable or unstable? Yes, it's stable because phosphorus or P comes from the third period. SF6, here sulfur has 12 electrons and again it's stable. This is all about Lewis structure. At home you can solve these four molecules, draw Lewis structures of them. The last topic in the chapter is the VSEPR model, valence shell electron pair repulsion model. What's the application of this model? Before talking about the details and how to apply the VSEPR model, let's take it or let's discuss it in terms of water. If I ask you to draw Lewis structure of water, you can provide this structure. Oxygen in the center, hydrogen left, hydrogen right. And you can write Lewis structure in any arrangement you want. You can write it like this. You write it like this. Nobody will ask you about the geometry. What I mean by geometry, geometry means the 3D sketch, the exact shape of the molecule. In Lewis structure, nobody will ask you about the exact shape or the 3D sketch or the geometry. You can draw as you want. But in valence shell electron pair repulsion theory, in this model, no, you have to provide the exact and the correct geometry of the molecule. In case of water, the correct geometry is V-shape. It's similar to the V letter in English. Now, how can we tell the exact geometry for any given molecule? This is our duty now. We will explain how to determine the geometry of the molecule. So read the question carefully. If the question just asks you to write Lewis structure, draw as you want, in any arrangement you want, in any geometry you want. But if the question asks you to determine or to identify the exact geometry, then you should apply the VSEPR model that I am going to explain right now. In VSEPR is used, as I said, to identify the geometry or the 3D sketch after drawing the most stable Lewis structure. So the first step in VSEPR is drawing the most stable Lewis structure. Most stable Lewis structure. After drawing this most stable Lewis structure, determine the type of your molecule in terms of EXNEM. What we mean by that? A is the central atom. You should always have A. Yani A, it's a fixed letter. Always write A. X is the number of outer atoms. Count how many outer atoms you have around your molecule. If you have 2 outer atoms, then the subscript is 2. It will be AX2. If you have 3 outer atoms, AX3. 4 outer atoms, AX4, and so on. E is the number of lone pairs of electrons around the central atoms. Lone pairs, not dots. Each 2 dot is 1 lone pair. So count how many lone pairs you have around the central atom. Example. Identify the AXNEM type of the following molecules. H2O. To identify the molecule or the type, as we said, you should first draw the most stable Lewis structure. Most stable Lewis structure. This is the most stable Lewis structure of water. A is the central atom. Here is A. X is the number of outer atoms. How many outer atoms we have around oxygen here? We have 2. So this is AX2. E is the number of lone pairs. Here we have 1 lone pair. And here is the second lone pair around the central. Don't forget, please. The number of lone pairs around central, not outer. So here we have 2 lone pairs. So the type is AX2E2. BH3. This is Lewis structure of BH3. A is always the same. A is fixed letter. How many outer atoms we have around boron? We have 3. So this is AX3. How many lone pairs of electrons around the central atom here? How many we have? We have none. We have 0. So don't write E. E is 0. It means that we don't have E's. So the type is AX3. For ozone, O3. This is Lewis structure. How many A's we have? We have one central atom here. This is A. How many outer atoms? We have 1 and 2. This is AX2. How many lone pairs around the central? Only around central. We have one lone pair. So this is AX2E. Then follow the table after determining the type in terms of X and E. Follow the next table. Not the slide 107. This is from, okay, ignore this. Follow the next table, the following table. Here is the table. This is the table. Can you see it? In this table, we have different columns. The first column is the group number. A group number. A group number is the summation of the subscripts. Again, to determine the VSEPR geometry, we said draw Lewis structure. After that, identify the type in terms of X and E. AX2E, AX3E, AX4, AX, whatever. Then follow the table. So we are here now. We have the type of the molecule. We already got it. And we are in the table. The group here means the summation of N plus M. N plus M. The summation of the subscripts X and E. AX2, the summation is 2 because E is 0. So 2 plus 0 is 0. So here we are in group 2. In group number 3, look, AX3, the summation of the subscripts is 3. And also we have one derivative from group number 3. It's AX2E. The summation of the subscripts of E and X. E is 1 and X is 2. 2 plus 1 is 3. So AX3 and AX2E both related to the same group, which is group number 3. Group number 4, it's AX4 or AX3E. Again here, check. The subscript of E is 1. The subscript of X is 3. 3 plus 1 is 4. Or AX2E2. 2 plus 2 is also 4. So those related to group number 4. For this course at Prince Sultan University, we will stop at group number 4. But in general, we have a group 5, group 6, and more. Okay, so but for our course, we'll stop at group number 4. So the type here, we already explained what we mean by type. The third column is a specific example. It doesn't mean that these are the only molecules that are related to the type. We have many, many other molecules, but this is just a representative example of each type. The fourth column is the molecular geometry, the name of the geometry, the name of the geometry. Linear, planar, triangular, V-shaped, tetrahedral, and so on. And here is the bond angle. Here is the bond angle. Now let's take an example. We have it already here in the table, but I prefer, as always, to start from the scratch. So let me redraw all of them. Here, the Lewis structure. Here, the type A, X, N, E, M. Here is the group number, whether it's group 2, 3, 4, etc. Here is the 3D sketch or the name of the geometry, molecular geometry name, the name of the molecular geometry. Here is, let's say what we have also, we have the 3D sketch, the 3D sketch, and here is the bond angles. The first example in this question is beryllium chloride, beryllium dichloride, BeCl2. When you draw Lewis structure for beryllium chloride, it will be like this: Cl, Cl. This is Lewis structure of beryllium chloride. What is the type of beryllium chloride? The type is AX2. We don't have any lone pairs around beryllium, so it's AX2. This is group number 2, the summation of X, the subscripts, excluding A, by the way, here. When I say the group number here, it's N plus M, the subscript of A, and E is not counted. Okay? So here, the group is group number 2, because the subscripts is 2. Molecular geometry. Any molecule of type AX2 has a linear geometry. So the name here of geometry is linear. What we mean by linear? Linear means line. So beryllium will be here in the center, Cl here and Cl there. And the angle is 180. This is what we mean by linear geometry. Another example, BF3. When you draw Lewis structure for BF3, it will be like this. So here the type is AX3, and this is from group number 3. Any molecule has AX3 type, then its molecular geometry called planar triangular or triangular planar. Planar triangular. Planar triangular. It's similar to the triangular, which means boron here in the center, fluorine, fluorine, and fluorine. Planar means all atoms lie on the same plane, on the board, or on the paper that you are drawing on. So here, the tablet, my tablet is the plane. All atoms are in the plane. So this is what I mean by planar triangular. And the angle is, as you know, if you have any circular shape, triangular, rectangular, etc., then the summation of all angles is 360. And here we have three angles, so 360 over 3 is 120. So here the angle is 120. The first derivative of AX3 is AX2E. This is the first derivative of group number 3. 2 plus 1 is 3. So they are the same in the same group. Example is sulfur dioxide. Sulfur dioxide, SO2. Lewis structure of SO2 is S, double bond O, sorry, and double bond O. And here lone pair. This is AX2P. Any molecule has AX2E type, it should have V shape geometry. V shape. It's similar to the V letter. Why it should have a V shape? Now look, when you compare AX3, this is AX3, with AX2E, what's the difference between them? As you can see, the difference is AX2 has two outer atoms with one lone pair, which means we replaced one outer atom of AX3 by a lone pair. So remove one of these outer atoms, this or that, any one of them. Here is sulfur, sorry. Here is sulfur, and here is oxygen, and here is the other oxygen. We remove this outer atom and we replace it by this lone pair of electrons. So the shape is V shape, upside down. طبعا V shape is upside down. This is still a V shape. This is a derivative of a group 3, so this angle should be similar or closer to 120. But what do you think? Is it 120 exactly, more or less? Now look, here we have lone pair of electrons. And the double bond here, the pi bond, it has electrons, right? What will happen between the lone pair of electrons and these electrons? Electrons with electrons, negative with negative. What will happen between them? Attraction or repulsion? Yes, we have a repulsion from this side. Repulsion. And we have a repulsion from the other side. So the angle will be compressed. So it will be less than 120. How much? We don't care about the exact value, but it should be less than 120, 115, 116, doesn't matter. But you should know that it's little bit less than 120 due to the repulsion between the lone pairs of electrons and the pi electrons of the bond. Another example. Let's take now CH4. When you draw Lewis structure for CH4, it will be like this. Carbon with 4 hydrogens around it. This is type 4. So it's AX4 from group number 4. Any molecule has type 4 or X4 type is called tetrahedral or tetrahedron. It has a tetrahedral shape or it is a tetrahedron. Tetrahedral shape. The geometry of tetrahedral, it's like this. Carbon here, hydrogen, and hydrogen. I don't know if you can imagine it or not, but if you view them from the next slides, you can get them more accurately because they are drawn in the next slides by the computer programs. So I think you can get the structure more clearly. But in tetrahedral structure, these three atoms, this hydrogen with this carbon and with this hydrogen, lie on the plane, on the surface of the paper. The third hydrogen, it's outside the plane, outside the plane. This is why I draw the bond using this bold line. And the fourth hydrogen is inside the plane. It's here. And the angle is 109.5. 109.5. This is the tetrahedral shape. The first derivative of AX4 is AX3E. AX3E. Example is ammonia and H3. When you draw the Lewis structure for ammonia, it will be like this. As you can see here, we have three outer atoms, so this is AX3. And we have one lone pair of electrons, so this is E, 1AX3. So this is group number 4. The name of the geometry for any molecule has AX3E type is called trigonal pyramidal or pyramidal trigonal. It doesn't matter. Trigonal pyramidal. Now ask yourself, what's the difference between AX4 and AX3E? Yes, we replaced one of the outer atoms by lone pair of electrons. So here we need to remove or to remove one of the outer atoms and to replace it by a lone pair of electrons. Then you will get the shape. So this is nitrogen here, hydrogen, hydrogen outside, and hydrogen inside. And replace one of the outer atoms, the fourth outer atom, by this lone pair. The angle, it should be very close to 109. But again, what do you think? Is it more or less 109? Yes, it's less due to the repulsion here. Repulsion from this side and repulsion from the other side, so the angle will be compressed. So this angle is a little bit smaller than 109.5. The last derivative of AX4 is AX2E2. Example is water. Lewis structure of water is O and H, as we said, in any direction. This is again from group number 4. The shape is V shape. Why V shape? Because now again we have to remove one of the outer atoms. Let's say this atom here, and put another lone pair, a second lone pair around the central atom. So here is oxygen, here is hydrogen, and here is the other hydrogen. This is the first lone pair, and this is the new lone pair, the second lone pair. So we again here we got a V shape. This angle, what do you think here, the repulsion compared with the ammonia, with the previous example, is it more or less repulsion? Yes, we have more repulsion because here the concentration of negative charge in oxygen is more. So the repulsion is stronger from left and stronger from right. So the angle will be compressed more. So this is less than 109.5. If the angle here is 104 or 5, this should be 102 or 3 or etc. This is how to draw the VSEPR, the valence shell electron pair repulsion model. You can view these examples from the next slide here more clearly and precisely because we draw them using the computer programs. Thank you very much.